Magnetic field force on a wire and between wires. Instead of just examining what happens to a moving charge in a magnetic field, let's take a whole bunch of charges, a constant flow of charges, otherwise known as a current, in a wire and see what happens. We introduced the horseshoe magnet in the last chapter. Now, every charge that moves will feel a magnetic force. So, you would expect the wire in which the charges move would feel a force in the same direction. As the charges are getting pushed, they're going to be pushing the other charges and atoms in the wire. So we're looking probably in the same direction the force is going to be. But let's think about it. Look at this picture to the right. The wire is in red. Here's the current flowing down, flowing across, and then flowing up. And then up here it's hooked to a battery or something. What are the magnetic forces on the three segments of the wire? You have this vertical piece of the wire, another vertical piece, and a horizontal. You have a uniform magnetic field going from north to south. We'll find the force on the wire by once again using the right-hand rule. But this time, place your fingers in the direction of the conventional current before you put it in the direction of the velocity of the positive charge. But since the positive charge velocity is the same direction as a conventional current, it's the same thing here. Then curl them into the magnetic field, just like you did for the moving charge, and then your thumb will point in the direction of the force. So we have three segments to worry about. Let's talk about the vertical segments first. And you can see up here, we put a battery, we put little pivots here for this wire here, so it can pivot about it, so it can swing. In this case, the current is in the absolute same direction as the magnetic field. That means zero magnetic force. They're parallel. How about this guy? Current's going this way, anti-parallel to the magnetic field, so the force is zero. The only force you feel is on this part of the wire. So when you put your fingers in the direction of the magnetic field, okay, you got your fingers like this, and then you curl them in the direction of the magnetic field, which is down. Let's see, it's hard to draw this. What you will have is your thumb now is going to come out of the board. That's the thumb coming out of the board. And here's the force. So the force on this piece of the loop is out. So the horizontal segment feels a force directed away from the magnet. And we have the battery and the two dots as pivot points. What do you think is going to happen to this current loop now? Again, summarizing, there's an outward force on this piece, no force on these two pieces. If you apply a force down here and these wires are free to pivot, this rod here, or this current carrying wire, will swing out. It'll keep going up until it no longer feels a magnetic field, and then gravity will pull it back. It'll probably push a little further back inside this until the magnetic field force once again pushes it out. So we have the thing kind of rocking back and forth. So what we've done is we took an electric current, a magnet, and started something rotating. Now, this isn't the best design in the world, it's just kind of a proof of concept. But what have we just invented? This is the beginning of a motor. Clearly, there's much more that you would have to do from an engineering perspective to make a real motor. Having a loop just go up and down isn't very valuable. Either in class now or for homework, look up how this configuration would be changed to make a real motor. Just Google motor. And while you're at it, you probably know that the earbuds from your cell phone have a tiny magnet in them. Look up how do music speakers work and see how this model works for producing music. The force on the wire depends on the current, the length of the wire subject to the magnetic field, and the magnetic field. Also the orientation. Once again, the only part of the magnetic field that contributes to the force is the part that is perpendicular to the current. So I is current, L is length of the wire, and B is the magnetic field. This actually comes from the QVB equation, the force on a charge. Because let's just look at a quick dimensional analysis here. Velocity is distance over time, and then we put the B here. Let's just rearrange these things. What's charge divided by time? Well, that would be I, right? Rate of charge over time. D we can call the length of the wire, and here's B. So that's a nice way to do it if you forget this equation. But here we go. This is a force on a current carrying wire. Force between two parallel wires. Set up two current carrying wires, each of length L, next to each other. Okay, so let's just start with that. Here's wire 1. See how the current I1 is going that way? Here's wire 2. They're parallel, and that's going that way. Each wire will generate a magnetic field. Now what happens if this wire is generating a magnetic field and this current carrying wire is within the field? It's going to feel a force. So let's start with finding the force on wire 2 due to wire 1. Well, we go back to our equation, and it's B1 equals mu 0 I1 over 2 pi d. That's the magnitude of this field, B1, at this distance here, d. And notice how all along this wire it feels the exact same field because it's at the same distance. And you can see how the field's going down. So let me just read this again just to make sure, because we want to stay up with this. The wires are separated by a distance d. The magnitude of the magnetic field generated by this wire that is over here near I2 is B1 is mu 0 I1 over 2 pi d. And that's the equation we gave last chapter for the magnetic field due to a current carrying wire. The magnetic field due to wire 1, here's the magnetic field due to wire 1, and if you look at this right here, this vector here, it's perpendicular to I2. So when I use the force on wire 2 due to wire 1, that would be I2, the current I2, times the length of wire 2 times the magnetic field due to B1. And since B1 is perpendicular, I can use the full value. Now I just found B1 on the previous slide. Okay, we found it was this. This is the magnetic field of wire 1 in the vicinity of wire 2. So I just plug it in. Now this doesn't look very elegant, so I'm just going to rearrange it a little bit so you can see some symmetry here. The force that wire 1 exerts on wire 2 is mu 0 I1 I2 over 2 pi d times the length. This is the length of the wires. We can do the same algebraic technique to find the force that wire 2 exerts on wire 1, or we can just invoke Newton's third law. It also works for magnetic and electrical forces, just like mechanical forces. And we will state that the magnitudes of the two forces are equal. And here are the magnitudes. And notice I show the vector notion of the forces. And their directions are opposite each other. Now we have to find out what is the direction of the force. Are the wires attracted or repelled? For example, you could have equal and opposite forces like that, according to Newton's third law. That's valid. Or the forces could be like this. Newton's third law is not telling us which ones they are, so we have to use another technique to find that out. If we want to find the force on wire 2 exerted by wire 1's magnetic field, we have to find out what direction the magnetic field is over here due to wire 1. Use the right-hand grip rule. Put your thumb in the direction of I1, and then curl your fingers about the wire, and you'll find that your fingers go into the page like that. So we now know that the magnetic field to the right of wire 1 is into the page. Now let's just get rid of this so we're not even thinking about that. Try and simplify. We now have a current in a magnetic field. We use the right-hand rule. We put our entire hand, all our fingers pointing up. Then we curl our forefingers into the page, into the magnetic field, and we stick our thumb out. And which way is our thumb pointing? To the left. So the force that 1 exerts on 2 is to the left. We now want to find the force on wire 1. So what kind of magnetic field does wire 2 generate in this area? Use the right-hand grip rule, thumb in the up direction, curl your fingers about the wire, and you find that on this side you have a magnetic field coming out of the page. Like we did on the previous page, the wire has done its job, we get rid of it. Now I use the right hand rule and I put my hand, my 4 fingers and thumb in the direction of the current. I curl my fingers out of the page and then stick my thumb out, and I find out that the thumb points this way. So remember, wire 1 is feeling a force in this direction, wire 2 is feeling a force in this direction, and they're the same magnitude, of course. So what we have is wires with parallel currents in the same direction attract. That seems odd, right? Because normally when we had a positive and a positive pole, they repel, a positive charge and two positive charges repel each other. But in this case, if the current's in the same direction, the wires attract. But what if the currents are in opposite directions? You probably already can guess the answer, but let's work it out anyway. Let's start to find the force on I2. Use the right-hand grip rule for wire 1. Magnetic field will be into the page. But now, when we look to find I2, the current is in the opposite direction, so when we use the right-hand rule, we find that the force is to the right. So you can start to see what's happening here. To find the force on wire 1, we use the right-hand grip rule for wire 2, and in this case we find the magnetic field is into the page. So now when I use the right-hand rule to find the force on I1, I find that the force is to the left. So wire 1, the force on wire 1 is to the left, the force on wire 2 is to the right. So what we have, which is what we guessed hopefully, is wires with parallel currents in the opposite direction repel each other. A straight long wire carries an electric current to the left. The current is placed in a uniform magnetic field directed out of the page. Out of the page, current to the left. What is the direction of the magnetic force on the current? Use the right-hand rule. Point the 4 fingers of your right hand in the direction of the current, which is to the left. Curl your fingers perpendicular to your palm and point them in the direction of the magnetic field, which is out of the page. Or you can just face your palm out of the page. Extend your thumb perpendicular to your fingers. It points in the direction of the magnetic force on a current-carrying wire, which is up. A wire carries a current of 5 amps in a direction perpendicular to a 0.56 Tesla magnetic field. What is the magnitude of the magnetic force acting on the 1.5 meter long wire? We have our givens right here, and since the magnetic field is perpendicular to the direction of the current, we can use FB equals ILB, or FILB. We substitute in our givens, and then we do the multiplication. We get a magnetic field force of 4.2 newtons. Example 3. What is the magnitude and direction of the magnetic force between 2 parallel wires 30 centimeters long and 5 centimeters apart if each carries a current of 40 amps in the same direction? First thing we have to do is be careful with our givens. The current, I1 and I2, they're both 40 amps, that's okay. But the distance was given in centimeters. We have to convert that to meters by moving the decimal 2 places to the left, and also the length of the wire, same deal. Okay, so now we can use our equation over here, which is a magnetic force between 2 wires, and substitute in our givens. So here's the currents. Okay, here's the length of the wire, here's the distance between the wires, and here's mu0. And isn't it nice? 2 pi just goes into 4 pi twice, so it makes the math a little easier. And we get a force of 1.9 times 10 to the minus 3 newtons. You can either use the right-hand grip rule and then the right-hand rule to find out what the direction of the force is on these 2 wires, or this is one of the few things I recommend you memorize. If you have 2 currents going in the same direction, they will feel an attractive force. So the direction of the force on each one is towards the middle here. They attract each other. If you have wires going in the opposite direction, if the currents are going in the opposite direction, they repel.